Okay. So who try to eavesdrop should not be able to understand. So basically, it's protecting data by converting it into a form unreadable by an eavesdropper, and only the authorized parties should be able to read it. So, can you guys name an example where crypto is used in real life? So maybe you guys could log into slido.com and type #crypto and maybe type in your answer. I'll wait for a minute. Do tell if you guys face an issue. Slido.com. You could just scan the QR code if you are using your mobile. Mm-hmm. So were you guys able to log in? Just type the code. Yeah. Crypto. No, not there. Yeah. So just name an example where crypto can be used in real life. You have a lot of examples around you. Anything is fine. It's fine if it's not, you feel it's stupid or anything. It doesn't matter. We all are beginners here. Yeah, end-to-end encryption, WhatsApp, Telegram. Okay. HTTPS. We got 3 responses here. Yeah, WhatsApp messages. Yeah, passwords are saved by encrypting them. Yeah, that's a nice example. Anything else? Only 4 people have responded till now. I guess we have more than 12 attendees, right? Yeah, we have like around 19 attendees. And only 4 people responded. Come on, guys. Yeah, authentication. Secured emails. Yeah, that's nice. Okay, 6 people. The count's going up. Yeah. So yeah, there was this WhatsApp issue, authentication, secured emails, online transaction. Yes, a very good example. SSH, yeah, that's nice. Okay. So yeah, so this is just to get an idea of whether you guys know where all crypto is used. I guess we can move on to the next slide. So before we move on, you guys might have a confusion as to what is encoding and encryption. So encryption is completely different from encoding, and you guys shouldn't confuse those stuff. So, what is encoding? Is just a way of representing data, and encryption is a way of hiding data. So basically, you might have to represent data in different formats according to use. So ASCII is an example of an encoding. So basically, each letter stands for a number. Here, small a to z stands for 97 to 122, capital A to z stands for 65 to 90, and so on. And for numbers, there are number encodings such as hex, base64, and binary. I've included some small scripts in the Colab to in Python, some snippets which can help you convert into encodings. For in Python, you have the OR function which is used to get the ASCII value of a. So you basically have to give a or the letter you want and run it, and you get the value. So then there is CHR, which is used to do the opposite. And I've written some codes where some interconversions. For example, hex, it is hex of then hello, yeah.
Could you please zoom your screen a bit so that it will be more clear?
Oh, yeah, sure. Okay. Is this enough or is it too much?
Yeah, it's good.
Okay. All right. So yeah, you guys can try it out simultaneously. Do you want me to wait a minute while you try it out? You can just go through it. I've included some basic examples. So here we would be using this in the future. So basically, if you want to convert a text into integer, so you use a module, you use two functions, bytes to long and long to bytes. It is part of a package called PyCrypto, which I had told to install earlier. It's already installed in Colab, so you don't have to worry. If it's not running, you can just click run all, and all the package dependencies would be installed. So bytes to long is used to convert a stream of bytes into long or integer, and long to bytes is used to do the vice versa. So this is the output. This you can just try running it. So back to our slides. So now you guys know what encoding is. Now let's go through what is encryption. So I assume you guys already attended Namita's session, the first session that she gave a basic walkthrough of what is Cesar Cipher. So anyways, let's go through it over again. So I don't know about you guys, but back when I was in school, we used to pass chits, like we used to write messages on a paper and pass it to our friend. So suppose two girls want to conduct a prank or something, and they write their message in a sheet of paper. Yeah, and there's a teacher watching over, so if she catches you, she shouldn't be able to understand the message as to what it is. All right. So what she does it, let's name her Alice. Okay. So Alice writes this message down, and she basically shifts each letter by 2. So A to C, T to V, T to V, A to C, C to E, etc. Everything by 2, and writes this down and sends it to her friend. So her friend knows that her friend's lucky number is 2, and so she shifts it back by 2 letters, and she gets the original plaintext. So even if the teacher catches the piece of paper or something, or she won't be able to understand. So if she looks at C, V, V, C, E, it doesn't make any sense, right? So yeah. So this encryption used here is called Cesar Cipher. So the person who is sending the message is called the sender, and the message which she sent we usually refer to as the plain text, and the process which she uses it to convert it from a sensible word to a random to some random characters is called and the final letters which she gets is called the ciphertext. Now we used 2 to shift it, right? So the 2 here is called the key. Now the teacher would be the eavesdropper, and finally she would get the message and she's a receiver. Now the process of converting the ciphertext back into the original message is called decryption. So I hope you guys are now familiar with the basic terms. So moving on, let's go through the classification of cryptosystems. So basically it's split into 2 categories: symmetric cryptosystems and asymmetric cryptosystems. So symmetric basically means you use the same key for encryption and for decryption. So if in the Cesar Cipher example, you remember that the first girl used Alice used 2 to shift it to the ciphertext, and Alice okay, I got confused with the name. So the friend uses the same key that is 2 to shift it back. So you use the same key for encryption and decryption. So that is what symmetric cipher means. In asymmetric, you have one key for encryption and a totally different key for decryption. So symmetric can be further classified into classical ciphers and modern ciphers. So the Cesar cipher we looked at is an example of a classical cipher. And the classical ciphers can be transposition, substitution, and so on. So modern ciphers can be stream ciphers or block ciphers. Stream cipher basically means you encrypt it character by character, and block cipher means even if you change one character in your plaintext, the entire ciphertext changes. Now, it's okay if you guys didn't understand everything. We'll be going through this in detail. We'll be looking through an example in almost each one of these categories. So let's go back to the Cesar cipher. So Cesar cipher is an example of a substitution cipher, which means each character would be mapped into its corresponding plaintext. So A would have a corresponding mapping, B would be having a corresponding mapping, etc. It has a symmetric key. That is, you use the same key for encryption and for decryption. The key space is 26. That is, there are only 26 possible characters in Cesar cipher if you just consider the letters, that is. So after 26, it just repeats again. So the key space is the possible number of keys. So the possible shifts are just 1 to 26. You can just do 26 shifts, right? Because there are only 26 letters in the alphabet. But is it secure? No. So what if I shift by 2 and you can just try 1, you can just try 2, and finally at one point you get the plain text. Now, so yeah, as I told you earlier, it comes under symmetric. It is a classical cipher and a substitution cipher. So next, there are some common attacks which are there on substitution ciphers. So first one is called frequency analysis. So what you basically do is you count the occurrence of each character in the plaintext. Now, according to statistics of common English words, E has the highest frequency in the English alphabet. Then comes T, A, O, I, N. So this is basically the order of frequency. So if you have, a para of ciphertext or something, you could just, or a very large piece of ciphertext, you can just count the characters in it. And if K is the most occurring character, then chances are that it, if X is the second largest occurring character, then it might map to T and so on. So that is what basically frequency analysis is. So the next attack is brute force attack. As I told you earlier, the key space is just 26 for Cesar cipher. So you can just brute force it. You can just try the key 0, then 1. In this example, the encrypted message is JX something. So you just try out the various keys 0, 1, 2, 3, and yeah, you get it at 3 itself, and the message is easy to break. So only the plaintext would have sense. So that is basically what is brute force attack. Thirdly, we have the known plaintext attack. So basically, if you know a particular character in the ciphertext to map to a corresponding character in the plaintext, then you can maybe judge the rest of it. So let's take the example of Cesar cipher here. So I know that A maps to C in the ciphertext. I only have the ciphertext, but I know that A is C. And this is an example of a substitution cipher. So what I need to do is I just need to subtract the difference here. So A minus C is basically 2. So I got the key and I can just use it to decrypt the entire message. So I just need to shift each character by 2 because I already got the key. I knew a part of the plaintext. So that is called known plaintext attack. So it's mainly used in substitution ciphers. So that's it about our basic Cesar cipher. Do you guys have any doubts? Is it all clear till now? Okay. Yeah, I guess I can move on to the next one. Okay. I'll continue. So, Zor is an example of a stream cipher. It's basically used in as the basis of all stream ciphers. It comes under the symmetric class. It's a modern cipher. It's basically the basis of all stream ciphers. So yeah. So what is Zor cipher? It's a stream cipher based on a logic gate. So for Yeah. So what is a Resor Gate? Resor Gate is a digital logic gate that gives a true output when the number of true inputs is odd. So if you, okay, let's just take A and B. So if the values are the same, you get 0. And if the values are different, you get 1. So that is how XOR gate functions. But how is it used for making a cipher? Let's have a look. So consider a small letter A, XOR capital. I take the binary of small letter A. So I told you earlier what different encodings are. So binary is an encoding where you everything is represented using just zeros and ones. So we first convert A to binary. The ASCII value of A is 97. So you get 11001. Now capital letter A would be 1001 or the values here. Now we use XOR it based on the concept we discussed earlier. If the values are same, if the bits are same, then it is 0. If the bits are different, it is 1. So finally we get 0, 1, 0, 0, 0. Now we convert it back to number and you get 32. And the ASCII value of 32 is a space. So the ciphertext we get here when we XOR this two is a space. So XOR can be of different types. It can be a single byte XOR or a multi-byte XOR. In single byte XOR, you basically use the same key for each and every character. All right. So yeah, you XOR each. Okay, this is our plaintext spaghetti, and you XOR it with the same key. So can any of you tell what is the issue if we use the same key everywhere? Anyone from the audience? Anyone? Okay. So basically what happens is if you use the same key,
I think
once
somebody was
it's similar to what you, oh, was
it was not
somebody
audible. So
talking? Was I not audible or?
no, I think
Am I audible now?
yeah, you are.
Yeah, you're audible.
If we get the key, then we can like decode the whole message in one go because because there's only one key, so we'll be able to solve it pretty quickly.
Yeah, very correct. So yeah, if you just basically get one key, then you can just decode everything. I'm sorry, decrypt everything. You should not confuse decode and decrypt. It's two different things. So yeah, this reduces the size of the key. However, yeah, the security is sacrificed. So I'll do one thing. I'll just increase the length of the key and maybe make it 3. So this is called a multi-byte XOR if the length of the key is more than 1. So yeah, this provides more security. So the XOR, it is XORed with an N. Again, this reduces the size. This increases the size of the key. However, it provides more security than a single byte XOR. However, this is not safe either. So because if we know the length of the key, all right, we can just group. So here I know, suppose I didn't know the key, but I know what the length of is. I know that the length is 3. So we can group every third character of the ciphertext and then brute force it. All right. So you'll brute force it. So I just group together the third characters and brute force it to get A. P, I can group all the second characters and group together to get B and C and so on. So that is the vulnerability of multi-byte XOR. So if you've understood this much, so what should be the ideal length of a XOR key for a plain text of size n? You can go to slido.com where this is active and maybe answer. I'll wait for a minute. It's okay if it's wrong. Everyone's learning, so yeah, it's fine. Are you guys able to join? Yeah. Okay, we've got 2 responses. Yeah, correct. Yeah, it's same as the plain text M. So yeah, so we won't be able to, even if we get one character, we won't be able to decrypt the rest. So yeah, that is the basis of XOR. If the key is same as this size of the plain text, then it's the strongest cipher ever. Okay. So now we'll be going through a video to understand what. Okay, wait. I guess I accidentally skipped a slide. Okay. So here I have two people. One is from London, Sharon is from London, and John is from India. So they don't have the key initially. How would they communicate? So they don't have the key initially. So Soumya would be, playing a video for you. It's from Khan Academy. Uh, I'll stop sharing the screen.
Yeah, sure. Give me a second.
Okay. I hope everything is clear. So we need some way by which we need to exchange the key. And we'll be discussing through the concept of how we would be able to do it through a simple example. Maybe put it on full screen. Yeah, your screen is visible. Maybe just put it on full screen. Yeah.
Up until the 1970s, cryptography had been based on symmetric keys. That is, the sender encrypts their message using a specific key, and the receiver decrypts using an identical key. As you may recall, encryption is a mapping from some message using a specific key to a ciphertext message. To decrypt a ciphertext, you use the same key to reverse the mapping. So, for Alice and Bob to communicate securely, they must first share identical keys. However, establishing a shared key is often impossible if Alice and Bob can't physically meet, or requires extra communications overhead when using the Diffie-Hellman key exchange. Plus, if Alice needs to communicate with multiple people, perhaps she's a bank, then she's going to have to exchange distinct keys with each person. Now she'll have to manage all of these keys and send thousands of messages just to establish them. Could there be a simpler way? In 1970, James Ellis, a British engineer and mathematician, was working on an idea for non-secret encryption. It's based on a simple yet clever concept. Lock and unlock are inverse operations. Alice could buy a lock, keep the key, and send the open lock to Bob. Bob then locks his message and sends it back to Alice. No keys are exchanged. This means she could publish the lock widely and let anyone in the world use it to send her a message. And she now only needs to keep track of a single key. Ellis never arrived at a mathematical solution, though he had an intuitive sense of how it should work. The idea is based on splitting a key into two parts, an encryption key and a decryption key. The decryption key performs the inverse or undo operation which was applied by the encryption key. To see how inverse keys could work, let's do a simplified example with colors. How could Bob send Alice a specific color without Eve, who is always listening, intercepting it? The inverse of some color is called a complementary color, which when added to it produces white, undoing the effect of the first color. In this example, we assume that mixing colors is a one-way function because it's fast to mix colors and output a third, and it's much slower to undo. Alice first generates her private key by randomly selecting a color, say red. Next, assume Alice uses a secret color machine to find the exact complement of her red, and nobody else has access to this. This results in cyan, which she sends to Bob as her public key. Let's say Bob wants to send a secret yellow to Alice. He mixes this with her public color and sends the resulting mixture back to Alice. Now, Alice adds her private color to Bob's mixture. This undoes the effect of her public color, leaving her with Bob's secret color. Notice Eve has no easy way to find Bob's yellow since she needs Alice's private red to do so. This is how it should work. However, a mathematical solution was needed to make this work in practice.
So, yeah, I'll go back to this. Okay. So basically, okay, did all of you guys understand the colors? I'm not sure if you guys understood it. So yeah. So if you go here, Alice basically has the red color is basically her private key. I'm audible, right? Hello.
Yeah, you are.
Yeah. Okay. So the red is basically her private key, and she finds the exact complement of the color, that is cyan, and sends it over to Bob. This will be her public key. Bob needs to send another color. So he'd mix the public key with yellow and then send it back to Alice. So even if the eavesdropper gets access to the green and also the public key, he won't be able to figure out what the original message was without her. So for this, we need a one-way function which we would use we need to create the private key, and we need to create the private key in such a way that even if we distribute the public key, an eavesdropper should not be able to find out what the private key is from. So let's move on to the next slide. So this is covered by RSA. So RSA is named after the three people who came up with the concept. So this comes under asymmetric crypto system. If you paid attention to the video, there are two different keys, one for encryption and one for decryption. It's based on, a little bit of math is going to come. So yeah, you might want to pay a little bit more attention here. So we need modulo, which is a one-way. So how is this used for? So 6 mod 5 is equal to 1, right? It's very easy to calculate. But if I say a modulus 5 equal to 1 and ask you what to say, there are different possible answers for it. 6, 11, 16, 21. And you won't be able to find out the inverse unless you have a particular information. And that is basically based on the complexity of prime factorization. So when you say the complexity of prime factorization, so suppose I give you a number and I tell you to tell me its prime factors, say for example 573 or 572. Now you might have to sit down and calculate what it is. So it's kind of difficult. But if I give you the factors and tell you to multiply it, you can do it in a matter of a few seconds or minutes. So you might argue that you could just write a small simple script in Python or any language of our choice to factorize it. But what if I say you have to factor a large number such as this will take the computer millions of years if you are doing a direct brute force. Now this principle is used to create our private. Let's see how. So the algorithm of RSA is basically divided into three. First, we generate the key, then encrypt and decrypt. So for it, we need to choose two large primes, P and Q. We choose primes because it would help us in the next. So, and you calculate the product that N equal to P into Q. And you also choose an exponent. will be a form like 2 power n. So here it is 6553. So the pair n comma e is called our public key. Just understand it for now. We'll see how it comes into use later. Now, in order to calculate our private, we introduce a variable called phi. Phi of n will be equal to the product of the factors p minus 1 into q minus 1. And d is determined as the modular inverse of e and phi of n. Should I take it a little slow? I mean, it's kind of a difficult concept to grab, I guess. So just understand that there's a function called modular inverse, and it's used to calculate e and phi of n. Notice that we can't know what is phi of n unless we know the factors. So d comma n, d will form the private key. Now, even if you know n, only if you factorize n to get its prime factors, will you be able to, get back our private key. So Alice could just distribute her public key, that is n comma e, and keep her private key. Now let's see how it is used to encrypt and decrypt messages. So for encrypting, you basically raise it to the power of e and mod it by n. So for those of you who don't know, modulus just means remainder, and decryption is basically power d mod n. So I wrote a simple script in the Colab in order to help you guys. Oh, I forgot to mention for Resor Cipher, I had included a small snippet, a small function in order to Zor it. You could maybe use it later. Yeah, anyway, moving on to asymmetric. Yes. For key generation, you use the module crypto util.number, and there is a function called getPrime, and 128 stands for the number of bits long the factors need to be. So the larger the bits, more the security. So p equal to get prime, q we get a prime, and n is equal to p into q. So we choose a prime because it's used to calculate the modular inverse. Okay, so these are our factors. You can try running it if you want. I'll pause for a bit. You could just open Colab. Okay, if you just get an error here, it's because you didn't run the earlier function. So you just need to go to runtime and do run all. So the earlier packages would be installed. So yeah, for a generation of private key, you calculate phi, and phi will be equal to p minus 1 into q minus 1. And you get d is equal to the inverse of e comma phi. And you just print it out. Yeah, the output is already there. Now for encryption. So remember earlier I told you a function called a bytes to long, which is used to convert our text into numbers. So we'll be using that here. So bytes to long, we'll convert our message into, and the cipher will be produced by raising m to the power e modulo n, and we'll get the cipher as follows. So you can just run it if you want. I have already run all this stuff, so yeah. And for decryption, you just need to raise it to the power of d. Now, notice that even if they get the ciphertext and n and e, unless you raise it to the power d, you won't be able to get back your original message. So once you raise the cipher to the power d, you basically get back the original message, and long to byte is used to convert the integer you got to a message. So the message will be printed as follows. Oh, I need to run all the above dependencies in order to get everything. Yeah, you basically just do run all. Yeah, so if you guys get an error, don't worry, just run the previous ones again and you'll get it. Yeah, so for decryption, once I run it, I'll get back my original message, that is, don't share my message. So let's take an example. Is this always our question, right? So we went through encryption, decryption. You guys can try out in your terminal if you want. You just need to install the dependencies mentioned in the Colab sheet. So is it safe? We are learning about cybersecurity, so safety is our main concern. So not always. The principle is kind of safe, but it might have some vulnerabilities depending on the keys we choose. There might be values of n such that n can be easily factored and you don't necessarily need to brute force it. So let's look at two examples. So the first case is when n is easily factorized. So if n is easily factorized, you can calculate p and q and get the value of d and get the message. So what happens is if p and q are a little bit close, instead of p into q, n will be equal to p into p plus r. And this r value will be really small in comparison to the value of p. So if we take the square root of n, the value we get will be approximately equal to p and will be somewhere near p. So what we do is we basically decrement the
Meenakshi,
p.
maybe pause a while and ask if
Yes.
there are some questions and if you need to repeat something before you go into the attacks of the specific. Yeah.
Is it clear till now? Anyone? Do I need to pause a little so that you guys can try running the commands here on your own? Anyone? It's okay if you want to pause. Maybe try running it. The encryption and decryption part. Yeah, sure. Hello?
Hello.
Yeah,
Hello.
you're audible. Hi.
I'm getting an error when I'm running, like I'm going into runtime and I'm running run all. Then I'm getting an error called no module named crypto.
You need to run a module called PyCrypto. Wait. Pip install. There's a command called pip install PyCrypto. You might need to just install it. Here, my requirement is already satisfied, so you can just install it. Just run that command.
Okay.
And
I
you'll
guess
get it.
I guess you can go on to the asymmetric key cryptography. Under that heading, there is RSA heading, subheading. So the first command, the first block would be of pip install pycrypto. Just run that command, and it should work. Yeah.
Okay. Any other doubts? Conceptually, is everything clear? I can explain it once more if you guys want. Anyone has any doubts? Okay, I'll take that as a no, maybe.
Please raise your hand, maybe like if you want her to
Yeah,
explain.
you could just raise your hand. There's an option. There's a symbol of a hand there in Teams, so you can just click it, and we can unmute you, and you can speak out. Okay. I guess we'll move on. All right. So we went through. Okay. So this is the first attacks when primes are kind of too close. So when it is close, it will be a product of p and p plus r, and this r value is going to be very small. So you basically, if you take the square root of p of n, you get an approximate value of p. Now we decrement it till we get the actual value of p. Let's see how that works. Now I've given the value of n, e, and c. I've pasted the same value in the Colab. Now you know that n is very weak. So you calculate the square root of it. GMPY is a module which can be used to calculate square roots, and other such stuff. For that also you need to install it using pip install. If you get some error message, there are a few commands which are in the top of the screen. Pip install. Just run these commands if you get an error that you are not able to install the module. Okay. So moving on, where is it? Okay. So this is our question. We have the public key, NE, and our ciphertext. All right. Now we know that the key N value is kind of weak. So what do? So we calculate the square root. We import the GMPY module and use its square root function to calculate the square root. There is also a square root function in math module, but the problem is you'll get it in terms of decimal. This will give the integer value rounded off. So while n is not a factor of p, you keep on decrementing p minus 1. So the loop will exit when it is a factor. So if you run it, yeah, you'll basically get the value of, oops, sorry, okay, I have to stop it. Okay, this will go on running forever if we don't execute this, because it will take the previous value of n. And as I told you earlier, if we try to brute force a value of n which is not weak, it will just run forever. Okay, so yeah, just run the previous module. And you will basically get the value of p. So this is the value of p. Now that we got one factor of p, q is n is just a product of p and q, right? So just divide it by p and you get the factors. Now you can calculate phi as p minus 1 into q minus 1. And from that you can calculate the inverse. And yeah, you can basically get the message by doing pow of c power the private key and modulo, and you get the message. Yeah, I'll just run it again. So this is our value of n, and the message is flag primes should not be close. So you guys can, I'll pause for a second and you guys can run it out if you want, or we can move on to the next session, whichever you guys want, next part. So this is basically it. Okay. Maybe I'll give the next question for you guys to solve. So so we calculated what happens if the primes are. Now what if e is really small, e equal to 3? Now if e is small, you're basically calculating m power e modulo n. And if n is a large value, there's a chance that m power e is less than n, right? So c will be same as m power e. And basically you just don't use the modulus there at all, because the value of e is small, and you can get c by just taking the root of c. So let's have the next question for you guys. So I've given the value of c, n, and e in the lab sheet. You guys can try it out. So n, e, and 3. Make sure you execute this, or it just takes the previous value which was executed and again starts running, and you might get some. So I'll pause for a minute and you guys can try it. Meanwhile, I'll explain it once more to people who didn't understand. So here you have the value of e, which is our exponent, n comma e is our public key value pair. I have given you n, however, m power e is really small. It's not very small, but it is smaller than n. So there is no effect of modulo. So if I tell you, okay, what is 2 modulo 6? 2 is less than 6, right? So it just gives you 2 itself. So there is no effect of the modulo. But if I tell you what is, if I ask you what is 7 modulo 6, it is 1. The value is changed, right? But if I take a value which is less than the modulo itself, you get back the same value. So there's a chance this might happen. If you take the value of E as 3. So basically here the ciphertext is same as the message. And you can just get the message by taking cube root of ciphertext. And for people who don't know, you can take the root by using gm. Gmk.root, there's a function called that. And if you want to see the solution, it's fine, it's just there. Okay, let's see if there are any answers yet. Oh, sorry. Okay, no responses till now. I guess we can walk through the solution. So basically, you can just calculate the root of m using the GMKY module, and you basically print out the flag. Can you guys try it out and maybe answer the put the answer there in Slido? Let's see if anyone has answered it yet. Yeah, there's one person. Maybe the rest of you can try to. I'll wait for 2 minutes. Just raise your hand if you didn't understand or you have a doubt or anything. I'll get to you. I know it can be a little bit overwhelming to see, such large, big numbers. But yeah, it's just a part of crypto and you might have to see even more. Okay, let's see the number of responses. We just have one response till now. You guys can look at the solution if you want. I've just written the script there. If you guys are facing some difficulties. So I just want to know if all of you have understood it and if you're really catching up with the session. You can also slow me down if I'm being slow, being too fast, or you can't understand my accent or anything like that. I can also explain it to you once more if you want. And if you want to explain it once more, you can just raise your.
Can you just explain the whole process in short, like not the whole process in detail, but in short?
Okay, I'll just basically explain what encryption and so you have a public key which is n comma e, all right? So n comma e is called the pub and d is our private key. Let's go back. So you'll be given n comma e, which is your public key, and d is something which you don't have, and that is calculated using the factors of n. If you remember earlier, d can be calculated only if we know the factors of n. And as I said earlier, you can't get the factors of p and q without, it takes a long time. So you need to know the factors in order to calculate the private key. So our aim is to get the factors. But here, even though the value of n is really strong, what happens is the value of e is really tiny. So for encryption, you do c equal to m raised to the power e and a modulo of n. And for decryption, you just raise it to the power d modulo mod. So what happens if e is equal? So c equal to just m mod n. So ciphertext basically becomes the same as message. And if m is smaller than n, then yeah, ciphertext is basically the same as message and there is no use. So if e is 2, you can calculate the square root and get the value of c. This is applicable if m is kind of less than n. And if it is 3, m power e is still less than n, you have to check if m power e is less than n. I'm sorry. Yeah, if e is 3, it will just probably be less than n. But if you take a value such as 65537 or something, if you raise a large number, it will be very big. So there is no chance you can get back the ciphertext. So here we chose the value of e as 3. So c is basically equal to m power 3. So you can get the ciphertext by simply taking a square root of it. Cube root of it. So let's see if anyone else has got the answer. Is that clear? Do I need to explain something else? Do I need to explain the previous one? Hello? This is fine, right? Okay, I hope it's fine.
Yes.
Okay. So just one response to now. Come on, guys, you can do it. I've given you the solution too. You just have to run it.
There is always an error message while running.
Okay, just
I
do run
also
all there.
Run all,
in-
as you said, Control
Yeah.
F9, still the coming an error message. But I think first we need to log in, because by my previous thing, we need to log in into the Google account, because otherwise it
Yeah.
doesn't even start running. So those of you who have no Google account, is not possible to use this. And then error message. Module not found, error.
Okay, can you tell me what the error message is so I can try to help you fix it?
Module not found error. So I can make a screenshot. Just wait a second.
Oh yeah, you can just send a screenshot or maybe do you want me to stop sharing so you can screen share?
No, I put it into the chat. Wait a second.
Yeah, ma'am, I was also having the same error. Then I go to the line number 36. If I run the line number 36 alone, like the first pip install crypto, then we don't get the error when we run the run all command.
Okay.
Okay, so can you try running line 36? I just pip install crypto. Maybe you just missed one of the installations. Yeah, this one. Is it this one?
Just a second.
Wait, I can't really see the message. Okay, continue with the basic principles. So yeah, okay, I will do it after this. Is it working for you, ma'am? Oh, okay. Okay, so this is the GMPY module. So if you go to the initial few lines of Colab,
I think you can just didn't run the import GMPY one. Like it says it's not defined, right?
okay. There are two possible sources of this error. One is that this command did not run properly, in which case GMPY was not installed. So you can try running this again and import GMPY. Where is the statement? There. Yeah, there is the import statement here. Okay. You did not execute this import GMPY because you didn't run the previous one, right? So you can either go run it or just insert a line there. Where you are trying out this question here. Yeah. So here you're using the GMPY module, but you didn't run the earlier installation one, right? So you can just go and type import GMPY here and then again run it. Don't forget to run this value of n, e, and c, or else it will just take the previous value of n and calculate, and you'll get some random junk like this. Is it working now, ma'am? Okay, if you guys have found the calculations to be really overwhelming, especially the first one, so you guys can go to a site called Factordb. So this site, what it does is basically if your key is weak, n is weak, it can factorize it. It works for small CTF challenges. Let me try the same thing, the previous one. So I copied the value here into this, and yeah, you can just factorize and get the result here. So you can use this for small CTFs where you might need to factorize in. Is the error fixed for you? Are you still facing any issues? Hello?
Yeah, I hear you. I just tried to run from the very beginning, so I think it takes some time. So you don't.
Okay.
So you can go further. Sorry.
Okay, it's okay. It's okay. Yeah, we just got one response till now, and I'll wait till everyone gets. At least we have like 3 to 4 responses. So yeah, maybe I'll run it for you, and yeah. Just don't worry if you get error messages. So the possible chances of error messages are if you didn't import a particular package. All right. So suppose you skip this and try to run this where this line was not there. So what happens is the previous line was not run, so it does not import it. So a module not found error would come. Or you might get another error where it is not installed. So you just need to run the line which says installed, and that would be fixed. And yeah, you might get some junk values like this if you forgot to run the previous one. So see here, I forgot to run N, E, and C, and I just run this. So the C was based on the previous value of C in the previous example, and that is why I got the junk value. So you need to run each step here. Okay. See? Okay. So our answer is flag E is too small. So that is what you're supposed to get here. So yeah, I guess there's still just one. Yeah. So one person has answered it. So the flag E is too small is the answer. So should I move or should I pause for a while for everyone to try out, or should I move on to the next? Just raise your hand if you want to pause a little bit more. Okay. I guess it's fine. If it's not fine, just please raise your hand and I can explain anything you want once more.
Meenakshi, I think you.
Okay, I'll continue then. Okay, so our next scheme is AES. So initially we discussed how we could, increase the ease of just encrypting by using RSA because you don't have to share keys and all. But the problem is, as you've seen in the two examples, only if you maintain a large value of n and e would you get more security. And if your ciphertext is and it's kind of really hard to calculate, and if you have seen, the computation takes a little bit of time too, right? So the larger the value of n, the more time it takes. So we need a cipher which in which the key size remains the same, and you just have to maintain a small key value, a constant key value. However, the encryption should also be strong enough. So we come to AES. It is a symmetric cipher, which means we use the same key for encryption and same key for decryption. It is a modern cipher and it is a block cipher. So what we mean by block cipher is, so in stream cipher, if you remember, we encrypted character by character. You saw the first letter with a key, second letter with a key, and so on. In block cipher, you just pass on the key and the entire ciphertext is changed. So even if you change one character in your plain text, the entire ciphertext will be changed. So it's a symmetric cipher. You basically have an encryption box. So the working of it is like really complex. It consists of a lot of shuffling and substitution, and you finally get the ciphertext. So for it, since it is block by block, you basically split it into blocks and pass it on to the encryption box. You provide the key and you get the ciphertext. So the basic structure of this remains the same. However, there are various modes in which we implement, for example, ECB, CBC, GCM, and so on. So ECB and CBC are kind of broken. GCM is kind of standard used now. So I'll be explaining ECB, just the basics of what it is. So this is the ECB mode. Here it is the simplest mode of AES. You basically split the plaintext into blocks of 16 characters each and pass it on to the block cipher, and you get the ciphertext. So this has a vulnerability. So what if both the blocks are same? So I would pass it on and get the ciphertext, right? But this both is kind of independent of each other. So if I split my ciphertext into blocks of 16, I can, realize if I can just judge if both are the same or not. So if I have the same blocks here and here, and if I get the same ciphertext together, it means that both these plaintext are the same. So we might be able to get some clue to the information of plaintext using the ECB mode. So in order to solve this, the CBC mode was introduced. So what they basically do is use XOR. There's a text called initialization vector, which is also 16 bytes in length. You basically XOR it with the plain text and pass it on to the encryption box, and you get the ciphertext. Now, for the next ciphertext, this ciphertext of the first block will be used as the IV of the second block, and it is XORed with here and passed on to the encryption box, and you get a ciphertext. However, this also has vulnerabilities. The attacks are kind of complex, so we won't be discussing it in this session. However, you are free to try it out on your own, and you can ask any doubts in Discord if it's there. So, is it clear till now? Do I need to explain it? So basically, I'll just go through the implementation of this in PyCrypto. So Python, you import a module called AES from crypto.cipher package. And we take it as this is a secret, and key is also a 16 byte character. And you create an object AES equal to AES.new key and the mode. So after you do these many steps, encryption is really simple. You just need to do cipher equal to AES.encrypt. And for decryption, you just need to do AES.decrypt. So let's try to run the code in the Colab. So this is our modern cipher, block cipher. So from crypto.cipher, you import the AES module. I have a secret. So this is a secret. So this is exactly 16 in character. So you encrypt it and you get the ciphertext. Now suppose I increase the secret to, increase it by 1 character. What do we get? You get an error, all right? And the error is basically because the length was small. So if you want a length greater than the block size, I might have to add some extra characters so that the length is an exact multiple of 16. Now if I add plus exclamation into 16, so basically I'm adding 16 extra characters. This will give the same answer, all right? So again, I'm just backspacing. You can just try with different values and experiment. So this is where we specify our mode, ECB. If we are using IV, you have to give the initialization vector too. Now for decryption, you just do message is equal to AES.decrypt. And yeah, you get back your original message. So that's it for the ciphers. So before we end the session, let me ask a question. So M1 this is a secret, okay? This is the this is the plain text. So cipher 1 is the encryption of this. M2 this is N secret, so I just changed A to N. And cipher 2 is the ciphertext of M2. So ideally, how would cipher 2 differ from cipher 1? So I've given you some options. You can just select whichever you think is appropriate. It can be none of the above two. I'll wait for a few minutes. Okay, we have one response. Come on guys, it's a multiple choice answer. You guys can do it. It's okay if it's wrong. We'll just try. We have 4 answers till now and 12 within the, more than 12 within the 5. Yeah, nice. Come on guys, you just need to, slido.com and /crypto. Yeah, that's the code. 7. Ten. Oh, nice. The numbers are increasing. Okay. Should I reveal the answer? Or, yeah, it's increasing. Okay. I won't tell the answer. Okay, 11. Okay. I'll wait for 5 more seconds and then we'll reveal the answer. Yeah, 12. Come on fast before I reveal the answer. 12. So 5, 4, 3, 2, 1. Okay, let's see. Okay. So the entire cipher text changes. 8% of you have answered the second one and other 8 have answered none of the above. So why is this answer correct? So this is because it's a block cipher, all right? So even if you change one character in the plain text, the entire cipher text would change, okay? So this is applicable only in the case of a stream cipher. The second answer is correct if I had used Zord or any other stream cipher instead of a block cipher. Okay, so that's it for the types of crypto systems. Now, yeah, moving on to the final phase, some tips and tricks to help you get started. So first is, Python is your tool. You can use any other programming language too, but Python is kind of simpler to use. So there are a lot of inbuilt libraries. There is something called SageMath which you can get familiar with in order to solve equations. So, yeah. So and you have to Google a lot when you don't know anything. You have to Google, and Googling skills is kind of really important. People who are into development might already know that. And if you're stuck, you can just ask a question, and nobody's want an expert. And it is really useful if you document your work via GitHub and follow the right blocks. And finally, yes, you need to practice and play more CTFs. Now, if you want to get some resources for how you can get started on crypto, Krypton is a library developed by our team member, alumni, Ashutosh Ahalya, and you can access it on github.com/Krypton. I'll be sharing the slides later. And if you like a war game kind of approach, you can always go for Crypto Hack. And obviously, you might get some past CTF challenges from CTF time or wherever it is. And you can always try those out. So that's for it. Yeah, that's for the session. Thank you. Yeah, that's all. Thank you. So do you guys have any doubts? That's, I guess I'll stop sharing the screen. Yeah. So I guess we are 10 minutes